Yes, Muhammad, that's correct. For your USDA soils classification, that's correct. Draw from clay to silt, silt to sand, sand to clay, correct. Please work on the workshop problems and let's review the solutions at 9:30. You have 5 minutes. Right, you'd like to review the solution. Problem 1.1. So saturated specimen tested in the lab. Weight before oven drying was 3 pound. Weight after oven drying was 2.5 pound. Oven temperature 110 degrees centigrade. Drying time 24 hours. Specific gravity 2.73. You need to calculate porosity, right? So the porosity is most nearly, let me see your answer. So majority 78, 79, 80% A, 20% C. Right, so whatever difference is here, because it was weight before oven drying, weight after oven drying means water has been evaporated. So whatever is different, that's the weight of water, right? And when sample was tested, that time sample was saturated. Volume of voids was completely filled with water, right? There was no air because sample was saturated. So under these things, we could work out void ratio E as moisture content, which is weight of water divided by weight of soil solid, multiplied by specific gravity divided by degree of saturation based upon table 1. Go to the table 1, look at the void ratio equation, and you can calculate the void ratio at 0.546. Some of you took this as an answer. Void ratio was not asked. What was asked was the porosity. Once you know the void ratio, then you can find the porosity, which is void ratio divided by 1 plus void ratio. If you do the math, you will get 0.353. Therefore, A is correct. Okay? Any question? Once the very good steam as sample is saturated, right? Whenever the word saturated is there, it means your volume of voids is completely filled with water, or degree of saturation is 1. Whenever the word saturated is there, the sample is fully saturated. So S is 1. If it is not 100% saturated, then problem should tell you it is 80% saturated, 90% saturated. It didn't say that, right? It said simply saturated specimen. It means volume of voids is completely filled with water. Therefore, degree of saturation is 1 or 100%. Okay? Problem 1.2. Project specifications for the construction of a highway embankment requires 125,000 cubic yards of fill material, and at that time your compacted dry unit weight of that soil is 112 pound per cubic feet. You need to bring the soil from the borrow sites, and the soil property at the borrow site is as given at void ratio was 0.8, specific gravity was 2.7, moisture content at that time at the borrow site was 15%. We assume there is no loss of moisture during transportation. Then what is the volume of soils you need to bring from the borrow sites, right? Or what is the volume that you need to transport from borrow sites to the construction site. So let me see your answer first. Okay, so everybody go with C, which should be correct, right? Because if you look at carefully here, the compacted volume is 125 cubic yard. At that time, your dry unit weight is 112. So compacted volumes multiplied by dry unit weight will give you the weight of soil solid. The weight of soil solid should remain same, right? Should remain constant. So at the bore sides, since the specific gravity is given, void ratio is given, and unit weight of water, you can assume it. Then you can calculate dry unit weight as this, which will give you 93.6 pound per cubic feet. Therefore, weight of soil solid at the bore site should be equal to the weight of soil solid at the construction site. Weight of soil solid at the bore site is V, that you need to calculate, and weight of dry unit over the soil at the bore site is 93.6. So 93.6 multiplied by V, which is weight of soil solid, should be equal to the weight of soil solid at the construction site, which is 125,000 times 112. Therefore, the total V is this divided by this, give you 149,572 cubic yard. Therefore, the closest answer is C. Some of you got D, right? Because of that 72. So this is 149,600. So the nearest number just above this would be 149,600. So we take C, not D, right? D is too far away. D is 150,000. So we'll stay with the C. Right answer, best answer is C. Problem 1.3. A soil sample weighing 5 pounds has a moisture content of 20%. How many pounds of water must be added to increase the moisture content to 30%? So let's see your answer first. Okay, majority I see is going for B. Again, the moisture content is weight of water divided by weight of soil solid, and weight of soil solid will remain constant because what is changing is amount of water. Change in amount of water will give you the change in moisture content. Any change in amount of water will change the moisture content. So in this case, the water that is need to be added to increase the moisture content from 20% to 30% is given by this equation, right? From 20% to 30%, when it was total weight was 5 pound, at that time moisture content was 20%. So if you work out, you will get 0.42 pound. If not, you could do the alternate solution, like at 20% weight of soil solid plus weight of water was 5 pound, because this is total weight. Therefore, weight of soil solid at 20% is calculated by these equations from table 1, give you 4.17 pound. Weight of soil solid will remain constant, right? Because soil is not being added, what is added is water. Therefore, total weight at 30% is weight of soil solid multiplied by 1 plus the moisture content to be reached, to be made, which is 30%. So 4.17 pound multiplied by 1 plus 30% give you 5.42. So this is at 30%, at 20% is 5 pound. Therefore, the difference is 0.42 O2. So this is the amount of water need to add it to bring the soil's moisture content from 20% to 30%. Okay. All right. Problem 1.4. A saturated soil sample has a porosity of 0.5, specific gravity of 2.65. Which of the following statements are true? Void ratio of the sample must be 1, the moisture content of the sample must be 62%, degree of saturation of the sample must be 100%. So these are the answers. Let me see your answer first. So this is the answer. Yes, Patrick, we're not adding any soil, we're adding water, right? The moisture content equations, weight of water divided weight of soil solid that you have written is moisture. So you have to make that moisture contents to increase from 20% to 30%. All right. So how you show that increment? The increment is shown as we went through in problem 1.3. Okay. What you have written there equation is perfectly correct. That's the equations of your moisture content. But that moisture content has to be increased from 30%, 20% to 30%. Solving for a weight of water there gets a value of 1.2. I don't know how did you get that one. Why didn't you send your calculations through email to me, then I'll go through it. Okay, very good. Good try. You have to try with different angle. Problem 1.2. I can see majority says B is correct. Then there are 20% with E, 24% with D. So again, the sample is saturated. So degree of saturation should be 1. Right? If you didn't know before, take it granted now. When the word saturated is there, that means degree of saturation is 1. That means volume of voids is completely filled with water. So porosity is given. Okay, if you look at here, porosity is given, N is given, not the void ratio. So since the porosity is given, calculate the void ratio, which is given by this. The void ratio is 1. So the statement B, which is true, right? And statement B, your moisture content is degree of saturation multiplied by void ratio multiplied by divided by specific gravity. Degree of saturation is 100%, so it's 1 in the calculation. Void ratio, we just got 1. Specific gravity is 2.65 multiplied by 100 give you 38%. So this is not 62%, this is 38%. So this statement is false. Statement C, degree of saturation, volume of water divided by volume of voids is 1, which is 100%. So statement 1 and 3 are true, but the B, second one is false. Therefore, the correct answer is C. But Titi, you have the old questions. That question has been modified. All right. So this question is asking for this. You have the old question. We modified that question. Before it was void ratio. So probably you have that questions, right? But now it is a new questions in terms of porosity. Okay. This is the new one. So both gives you this void ratio. Yes, for the old one, I do agree. It was D. No. Old is void ratio, new should be porosity. Alright. Because I made this question, so I know. So there should be a switch. Anyway, what is important is you have to be able to use the tables to calculate whether it is porosity or void ratio. Okay, let's not go with these things. You have to know, go to the tables and get the correct equations to calculate whether it is porosity or void ratio. If you want to take a shot, take a shot here now. I changed that from void ratio to porosity, so that you have to calculate one more step. Okay. Answer is C, because statement number 1 and number 3 is correct, but the number 2 is not correct. In number 2 we got 38%, right? 38%, but the answer here is 62%. Therefore statement C is correct. This is true, this is true. E is not true, therefore C is correct. Luis, okay? Very good. Okay. Problem 2.1. Sieve sizes are given here. Liquid limit, plastic limit, water limits are given here. Sample A percentage fire is given here. You need to classify soil sample A using USCS classifications. Okay. So let me see your answer. Khalif, if you want to take the snapshots, please take it. This is the new problem. Okay. But as I'm emphasizing you, whether it is void ratio porosity is perfectly fine. Whatever is given in the exams, if it is in the exams, you have to be careful with that word. The main thing is how to calculate porosity or void ratio by looking at the parameter given here and using the table 1. Okay, that was the main thing. If you want to take a snapshot of this problem 1.4, you can take it. Let's 2.1. I was looking for your answers. There are majority are saying this is B. Okay, and there are 20%, 80% saying B, 20% saying A. So before solving it, let's say it. What you have been asked to classify the soil sample A is based upon a USCS system. Is A USCS system? No, right? If A is no USCS system, then A cannot be the answer. Similarly, is C USCS system? So C cannot be also the answer. Possible answer is either B or D. If you look at answers B or D, the first letter is S, first letter is sand. So this means for both B and D, first letter is sand, means a major fraction of the soil is sand. In case of B, it contains clay. In case of D, it is clean. It contains very, very less fine. It's well-graded sand. It has got coarse sand, it got medium sand, it got fine sands, everything. But this sand has got more clay. So if you are expert, you can look at here, percentage passing to number 200 save is 35%. So the B should be correct, but we have to do the problem, right? So let's look at the problem. A cannot be the answer because this is not USCS system. C cannot be the answer. This is not a USCS system. Therefore, in the classification procedures, liquid limit is given 40, plastic limit is given 14. Therefore, PI is 26. And percentage passing through number 200 sieve is less than 50%. Only 35% is passing. Therefore, it is a coarse grained soil. So if you go to the figure 2.4, then we can plot liquid limit versus PI value. The coarse grains percentage of gravel is 15% and percentage of sand is 50%, right? Therefore, this is a major fraction is sand, or sand fraction is more than gravel fraction. So we'll pick up this flow chart. Sand fraction is greater than gravel fractions, and your fine is 35% there, right? Your fine is 35%, so which means greater than 12%. So you have to go from here to here. So see, your fine is 35%, so go from here to here. So once you go, you need to plot the cascade plasticity chart. As you know, this is the sand fraction is more than gravel fractions. So all the first letter of all of these symbols is S, right? So we're looking for the second one. So from here, bring the cascade and plasticity charts, plot the value of liquid limit is equal to 40 here, and plasticity index is 26, right? So 26, if you plot the point lies here, it means we'll go for the inorganic soil, that is Cl. So here, Cl or Ch, so you have to move from there to here. So if you move there, your soil is Sc. This is how you classify, Okay, Khalib, I will tell the School of PE to give you that, alright? You can work on your own when you get it, and if you still have problems, let me know. It's questions of porosity versus void ratio. Don't get crazy. Concept is same. That's the main thing here. Our purpose here is to learn. Okay, you have been working on that void ratio for many years, so I converted that void ratio to the porosity. Rather than void ratio being given, if you are given porosity, still the concept is same. That's what you should be able to do. All right. Please stay with the class. If you still have any problems, I will take the problems, questions. If you want to go over that again, I can go with you that, but do not hold the class. Let the class finish. After 10:30, I will take your questions. All right. If you are not happy with it, I can answer you. So answers is B. So 80% was correct. Problem 2.2. These are your sieve sizes given here, and sample percentage values are given here. Now you have to use the as to, alright? So if it is as to, then obviously A cannot be the answers, B cannot be the answers, because these are USCS system. As to will have first letter A, right? So this is your answers, this could be your answers. So let me see your answer first. So majority is saying it should be D. C is also A-7, D is also A-7. So what is the difference? Calculate the PI of this soil. What is the PI of this soil? Can you tell me? 33. And what is your testing value? Liquid limit minus 30. What is that value? 25, right? So PI is 33, testing value is 25. So PI is greater than liquid limit minus 30. Therefore, it should be A-7-6. That's what the table below the ASTO tell us, right? So let's see it here. when you put liquid limit is equal to 55, this is 50, 60, 55 here, and PI value is 33, that is your 30, that's your 35 here, right? So your point lies here, therefore it is A-7-6. Okay, if you want to do the table using the process of eliminations, you can do it, you will end up to the same answer. But looking at the answers is A-7-5, A-7-6. Only difference between them is that compare the value of PI to the liquid limit minus 30, then you can tell whether it is A-7-5 or A-7-6. In this case, PI of the soil is greater than liquid limit minus 30 value, therefore the soil is A-7-6. And by plot also, you can see this is A-7-6. Your answer is D. Okay. Problem 2.3. The result of a sieve analysis for a soil sample are shown below. These are the sieve sizes, these are percentage finer, and these are the answers. Let me see your answer first. So I can say 65% with B, going with high plastic clay, right? So one thing is here, 55% is passing through number 200 sieve. So this is a fine grain soil or coarse grain soil? It is a fine grain soil, right? If it is fine grain soil, then M is silt, so this is possible answer. B is clay, first letter is clay, so possible answer. C and D cannot be the answer because C the first letter is sand, D the first letter is sand, but 55% is passing, therefore C and D cannot be the answer. This is how you eliminate the wrong answers. Okay, between A and B you need to plot it now. When you plot it, the point lies here. Some of you may have taken MH, some of you may have taken CS. Since it is light on the line, you will move toward the higher side, so we'll keep the answer as CH. Okay, that's why majority of you got CS, but some of you got MH. So those who has taken it as a MH, since it is light on this line A, because line A has equations given here. If you use that equation of the line, put the value of liquid limit, you will get 26 and PI value is 26. That means PI lies on this line, that means move toward the higher side. Okay, therefore the answer is CH. Really looks like MH. Why is that, Tim? Your calculations gave you I got CH, but the chart said if it was CH or CL. Why is that? I got CS, but the chart said if it were CH or CL, it is SC. Why it's SC? Why you have to go to SC? When percentage passing to number 200 sieve is more than 50%, then it cannot. You don't need the flow chart. You will need the flow chart only when percentage passing to number 200 sieve is less than 50% and it is a coarse grain soil. And at that can it could have a sand fraction more or gravel fraction more, whichever more you will find the flow chart. In that flow chart you will need Cassegrain chart, but here more than 50% passing, you will use the Cassegrain chart directly. Okay. Yes, team, I 100% agree. Interest, because your logic is you will get 26.2 or something like that, right? So that means PI value is the line is a little bit higher. But if you look at the principle of significant digits, two significant digits, then I would say it's 26 or 26.2. Take it as a 26, and I would say it lies on the line. So anyway, it's very good discussions. Wherever you are on the line, you are better off as engineers to go to the higher side. Okay, so you will classify the soil as CH. Problems 2.4. The gradation curve is given here and the sieve sizes are given here. Liquid limit is 40, plastic limit is 30. You need to classify these soils based upon USCS classification system. When you look at here, all the answers belongs to USCS system, so they are valid. And also other thing is, if you look at S, G, G, S, this should be a coarse grain soil. It cannot be a fine grain soil, right? None of the first letter is M or C. M or C is only your second letter. The first letter is either S or G. Therefore, to look at the percentage passing the number 200 sieve, I think before that, let me see your answer. We have 65% with B. That's the majority. So it should be GM. When you say it, it should be silty gravel, right? Gravel is a major fractions, major portions, and silty is your minor fractions. But when you pronounce it, it should be silty gravel. So anyway, let's do the solution. First of all, draw a vertical line for number 200 to the given curve to lead the percentage passing. So it means 42% is passing through number 200 sieves and 58% is not passing. Out of that 58%, percentage passing through number 4 sieves, I can draw a vertical line on the curve and read the percentage passing is 67. So 67% is passing through number 4 sieve. Therefore, the percentage not passing through number 4 sieve is 100 minus 67 is 33, and sand is 67 minus 42 is 25, and fine is 42. Therefore, your percentage passing through number 200 sieve is 42, and percentage not passing through number 200 sieve is 58%. Out of that 58%, 33% is gravel, 25% is sand. Therefore, you have to go to the coarse fraction, and in the coarse fractions, gravel fractions is higher than sand fractions. So you have to pick up the chart which says gravel fraction is more than sand fractions. Then look at the fine there, right? So it's 42%, which is greater than 12%. So you'll move from there to there, and here you will need category chart. So if you plot here, liquid limit is 40, PI is 10. So your point of intersection is here. So this point lies here, so this means your swell is ML. Means in this case, you will follow this line from here to here, ML. Therefore, your swell is GM. Solution's answer is B. Okay. Very good questions. Muhammad is telling, rather than percentage finals, if there is percentage retain. If they trick you, no problem. Percentage retain is just okay. Let me show you that. That's a good point. That first will be so here. This is percentage passing, right? This is percentage finer. If percentage retains, maybe they could give it here. Then percentage retain is 100 minus whatever percentage passing is given here. So instead of percentage passing, if it is percentage retain, then it will be 100 minus 0. Percentage will be 100, 80, 60, 40, 20, and 0. Just opposite. It's a mirror It's the opposite side of the things. All right, retain will be 100 minus percentage passing will give you the percentage retain. Or if percentage retain is given, what you need is the percentage finer. So percentage retain minus 100 give you the percentage finer by weight. If it was a retain, then it would be 40% here, because 100 minus 40 is 60. So percentage passing is 60, percentage retain is 40. If it is a percentage retain, then in this case it will be 60. 100 minus 40 is 60. So this is how you should know, okay? They will tell you percentage passing or percentage retain. They will tell you. That they cannot trick you. Jeffrey, okay? Very good. Let's move on. We are running out of time. If we leave behind a lot of things, then tomorrow, day after tomorrow, we have to run very quick. So let's go over chapter 3 now. Where is okay, the chapter 3 talks about soil sampling. To understand the behavior of soil, to understand the parameters to be used for the designs, we need to do the lab testing. For lab testing, we'll need soil sample. And soil samples, the technique to obtain sampling is two techniques. One technique is undisturbed samples, because sometimes you will need undisturbed sample, sometimes you could use disturbed sample. Undisturbed sample, as defined, is related to the sample which keep the in situ structure of the soil intact. Okay, and for the fine grained soil such as your clay, the undisturbed sample is obtained by using the Selby tube, thin wall Selby tube as given here. Picture of thin wall tube is given here, and it has to have, that tube has to have a requirement which is the area ratio requirement. This area ratio requirement should be less than 10%, which is given as outer diameter square minus inner diameter square of that tube divided by inner diameter square of the tube. Other technique to obtain undisturbed samples are also given here, which is thin wall piston sampler or block sampling, very big block. Or if you need to obtain the undisturbed sample of the granular material such as sand, then other technique involved could be ground freezing technique. You freeze the ground and take the samples, in which case the in-situ structure of the particles will be intact. But ground freezing is a pretty expensive thing, but that's the one of the technique. For the fine grained soil, you can use the Selby tube. For the coarse grained soils, you can freeze the ground, right? If you are running a tunneling projects or very important projects, you need to designs, you need the soil parameter to designs, then you may have to freeze the grounds and obtain the samples. Okay. Now, other is disturbed samples. There are many soil parameters you can obtain or determine by using disturbed samples. One of the procedure to obtain disturbed samples is while performing standard penetration test. At the standard penetration test can give you the disturbed sample. This is a standard penetration test split is to sampler, and in this split to sampler, this is your soil samples here, which is a disturbed one, right? As shown here. In case of rock, to describe the rock, you need to calculate the RQD, and RQD is defined as summation of all the pieces which are greater than or longer than 100 millimeters, or in SI unit longer than 4 inches, divided by the length of the core advance. So the photo here on your right indicates the rock core. These are your rock core, right? Rock pieces here, different pieces. So you will add all the pieces longer than 4 inches when measured from center to center, right? Center to center. All the rock pieces longer than 4 inches, you will add them together and divide by the core run. Again, core run is the actual core you have run in the field. When you take this rock core, the rock core, these are your retrieve or recovery rock sample, rock core sample recovery. Rock core recovery. Recovery may not be equal to the length of core advance. Usually it is less than that, right? In case of soil also, you saw that this is the spiritual sampler, but you only obtain this length of the sample. This is gap here. Okay, it doesn't mean that soil has a gap. It means that these techniques will obtain only the part of the soil in it. Similarly, part of the rock in the rock core sample. So based upon RQD, rock will be defined as very poor, poor, fair, good, and excellent based upon this RQD. This is a table which summarizes the common field test, the test performed in the field to obtain the soil parameter for design. So the test could be standard penetration test, cone penetration test, field vane test, and table here talks about what type of soil are suitable to conduct this test, and what type of soils are not suitable to perform this test, and based upon this test, what kind of soil properties can be estimated or determined is given here. Furthermore, this is pressure meter test and dialectometer test, right? It's given here, and these are the parameters we can determine from here. And these numbers belongs to ASTM number. For a standard penetration test, designated ASTM number is D1586. Cone penetration test is this. Field vane test, pressure meter test, and dialectometer test, also known as flat plate dialectometer test. This is a common institute test for geotechnical site characterizations. So this indicates the standard penetration test. This is your cone penetration test. This is your dialectometer test. This is your pressure meter test. This is vane shear test. So for the standard penetration test, you need to drill to the depth from below which you need to find the N values, right? So drill there and you'll bang with the 140-pound hammers falling from a height of 30 inch and counts the number of blows for first increment, second increment, third increment, and so on. Okay. Cone penetration test is a continuous process. Usually it is performed from the truck. From the truck you will push the cones and you will obtain the tip resistance as well as the sleeve resistance of this cone as well as port pressure also. Anyway, you can obtain the value using this cone, and this is a very good technique to profile the subsurface condition continuously. This is the dialectometer test. If you need to know the lateral deformations, this is a very good test to be performed. Again, this is a direct push, so the ground has to be soft, right? For cone penetration test and dialectometer test, if there are rock or gravels, then these cannot be performed. So from dialectometer test, you can push it and you can check the lateral deformations or many other properties as given in that table. This is pressure meter test. It is, since you are drilling here, you will drill down to the required depth. So even if the ground is hard, you can drill down, you can case the hole, then send the pressure meters. Again, you can determine the lateral stiffness of the soils or lateral pressures of the soils here. Field vane test. Again, if the ground is hard, you can drill down and push this vane and shear the vane from the top. This will give you the undrained shear strength of the soil there. So these are some pictorials diagrams to understand the in situ test. Out of those tests, standard penetration test is very popular and used in the United States to most of the time for the subsurface profiling. This test involves driving a spoon of 140 pounds, dropping from a height of 30 inches, and this test involves driving hammer 3 or 4 consecutive increment of 6 inches into the undisturbed soil. The field N value is always taken as the number of blows for the second increment and third increment. Second increment is from 6 to 12, third increment is from 12 to 18. That represents the blows per foot. 6 inch plus 6 inches is 1 foot, right? Field measure N values are subject to the error pertaining to the equipment, rig, and the operator. Therefore, you need to apply the energy correction factors. So Nm is the field measure N value. When you apply the energy correction factors, that is E divided by 60, give you the energy corrected N values. That energy correction factors could be if your operators or if your system is giving only 60% efficiency, then energy correction factor will be 60%. If it is given 70%, 70%, or 80, and so on, right? This value will be given. But for your case, unless they tell you to apply the energy correction factor, do not apply this energy correction factor, right? You will take the field measure N value itself as your N value. And also for the granular soil such as sand, you need to apply the overburden correction factors, which is given here, under root PA divided by sigma dash B. PA is atmospheric pressures equal to 2000 psf, and sigma dash B is effective overburden pressure. We will talk about effective overburden pressure tomorrow in chapter 6. This is again schematic diagrams to show the sequence of driving the split system sampler. So let's say you need to take the N values below this point. So you will drill down here, you will case the hole, and you will send that split system sampler, then bank with 140 pound falling from a height of 30 inches. Then you will count the blow count for first increment, 0 to 6 inch, second increment, 6 to 12 inch, and third increment, 12 to 18 inch, right? Your N value is always for the blow count for second increment, advancing second increment, and the blow count required to advance third increment. These days, even we take for the fourth number also. Okay? But in either case, whether it is a 3 sequence number or 4 sequence number, your N values is the blow count required to drive second increment and third increment. So for example, in this example, if a split test yield the following data, what is the N values? First increment 0 to 6 inch took 3 blows, second increment 6 to 12 inch took 7 blows, third increment 12 to 18 inch took 6 blows, fourth 12 to 24, 9 inches, right? In that case, your N values is number of blows to advance second increment and third increment, which is 6 to 12, 12 to 18, that therefore 7 plus 6 is 13 N value for this example. Standard penetration test N value, this is given with the energy correction factor, but we can take it as N values also, right? This is for your fine grained soil, such as your silt and clay, or fraction passing through number 200 sieve. Fine grained soil, the unconfining compressive strength Q sub U is given in terms of KSF and kilopascal here, and based upon the N value, you can describe the fine grained soil as a very soft, medium, steep, or very steep and hard, like this here, as shown here. Okay. And note N60, this value should not be used to determine the design strength of the fine grained soil. You have to use the N value itself, right? Now, for the granular soils, for your sand and gravel, based upon N values, the relative density that we talk in the chapter 2 or chapter 1, relative density, it could be termed as a very loose, medium, dense, or very dense. And based upon the relative density, the friction angle varies as shown here. These are the two type of recessor A, recessor B, right? It could be Terzaghi, it could be Meyerhof. There are different schools. Based upon that, the friction angle is given. So the friction angle is for the very loose is less than 28 or less than 30, right? Or for the loose, it varies from 28 to 35 for both for A and B. So you can have lower value and higher value. So this again, the relative density increases, your friction angle also increases there, right? So when the relative density is increasing, when the N value increases, relative density increases, then your friction angle increases. In exams, they may ask you to interpret the boring log. So if boring log is given to you, you should be able to read the boring log and find the values or parameters given in the boring log to answer you. So let's take an example. This is a typical example of a boring log. Your projects, weather, all the logistical information will be given here, and actual testings information will be given here. This reference to the depth below the ground surface, and this refer to the elevation, right? At that depth, what are the elevation? And this, in this particular boring log, is given the information of the water level in the boreholes. And soil classification based on USCS systems. Here it could be based upon ASTO also, right? And graphical representations of that soils. And this is important. This talks about the details about the soils type in every strata underneath. And this indicates the sample number 1, sample number 2, and this indicates the type of samples used. SS stand for split spoon, ST stand for Selby tube. And this says recovery. Your split spoon sampler is 2 feet long, which is 24 inch. Out of 24 inch, in this case, this represents 18 inch of recovery. In this Selby tube, it recovered 23 inch of sample, undisturbed sample. These are your blow count number, and these are the values determined in the lab: moisture content, dry unit weight, and this is your unconfined compressive strength, Q sub P, right? Unconfined compressive in terms of THF. In this particular boring log, it could be KSF, it could be TSF, but here it is given a TSF, and these are against the liquid limit plus limit PI value determined in the lab. This is information. Another, if you look further, you can see everything same. Water table here, after the completion went up to there. During the drilling, water level was here. And rest of the thing, again, your sample number 3, sample number 4, sample number 5, all were SS. That means split spoon sampler. And these are your blow counts, right? So if you look further down of the same page, same boring log, then you can find here sample number 7, use the split spoon sampler, and the sample recover was sample recovers were 13 inch, but it went up to what, first 6 inch it went to 28, it took 28 blows. The second one it took 50 blows, but just went 2 inches. So it says underneath this there is a very hard strata, so you will call it as a refusal. And in this boring log, they core it from elevation 750 to 745 now, right? 745, it was recorded as limestone grade slightly fractures, and they use DC, means diamond core barrel, and your recovery was 52 inch. So out of 60 inch, 5, your diamond core barrel rock cores are core in 5 foot length. Out of 5 foot 60 inch, the rock core recover what, 52 inch. Then RQT is already given here, okay, is 62%. Why does the water level changes? That's what's happened in the field. Gyro, okay, water level changes during the boring, so it moved down, then after that it bounced back. So usually when you have a water levels, when you have a well in the borehole, after 24 hours you will go and check the actual water level. So during the drilling it will change. Mohammed says because of the Venturi effect. That Venturi is coming from hydraulics, right? Okay, so move on. So the examples or the questions could be something like this. Let's say, use the boring log in figure 3.3 shown on the previous page to answer the following. Less the question asks is the best estimate of the shear strength parameter friction angle phi of the sand layer encountered at elevation 776.5 to elevation 771.5. Okay, so these are the probable answers. So if you look at here, this is your sand, 776.5 to 771.5, right? So this is sand. If you look at here, what is the n values for this sand? Can you tell me? What is the n value for this sand? It's 12, right? Because it says 4 for first increment, 5 for second increment, 7 for third. So always for second and third, 5 plus 7 is 12. So your n value is 12. So if you look at here, when your n value is 12, that means between 10 and 30, right? So that means relative density is medium, but it didn't ask. What it asks is, what is the friction angle? Friction angle. So for the medium dense sands, friction angles varies from 30 to 40. According to A, it varies from 30 to 36. According to B, it varies from 35 to 40. So ultimately, it varies from 30 to 40. If you look at the answers, this is 28, cannot be the answers. 35 is the answers, because C is 42, greater than 40. D is 49, greater than 40. Therefore, B is the correct answer. So this is how you will answer it. Again, B. Estimated unconfined compressive strain in KSF of the fat clay encountered at a depth of 3.5 to 8.5 feet is most likely. So, if you know unconfined compressive strain is given here, then you can solve it in 1 minute, very quick, right? But if you don't know what is unconfined stress given, then you will spend a lot of time here. So that's why when you read the boring log, make sure what are the things and that's presented in the boring log and where it is kept. So for our case, for the fat, this is your lean clay and this is your fat clay, right? What is the fat clay? Fat clay is given as CH. What is the lean clay? Lean clay is given as CL. Low plastic clay are known as lean clay and high plastic clay are known as fat clay. Okay, so keep this also in mind. Fat clay means high plastic clay, lean clay means low plastic clay. Now the question asks is for the fat clay, so we are looking at here. Here your unconfined compressive strength is 0.25 TSF, ton per square feet, and we know 1 ton is 2 KSF, right? So 1 TSF, 1 ton is 2 kips, therefore 0.25 ton per square feet is 0.5 KSF. So that should be the answer, because if you look at here, it is in KSF and this is given in TSF. So ton has to be multiplied by 2 to convert into kips. So 0.25 multiplied by 2 gives you 0.5 kips. So the A is correct answer. C. Which rock quality descriptions from best describe the limestone encountered at a depth of 35 feet? So here it is your limestones. RQD is already given, you don't have to calculate it. So if you look at the table here, when your RQD is 62%, that lies between 50 and 75. Therefore, your rock is a fair. So your answer should be B, right there. Right? So these are the typical questions based upon the boring log. Again, this is the table telling you about the laboratory test. We have the table with the field test. We also have the table for the laboratory test. For the laboratory test, these are the type of test and what type of soils are, whether you need disturbed sample or undisturbed samples is given here, and it is appropriate for what type of soil it is given here. And the properties that can be measured or determined by performing this test is given here. Right? You can read it here, or if you need it, it's given in this table here. Furthermore, these are the different tests here. So that will end our chapter 3. Time now is 10:30, so I will not be able to take the chapter 4 today. So tomorrow I will start, we'll go over the chapter 4. Okay, and once we finish chapter 4, we will go over the workshop problem of chapter 3 and chapter 4. If you want, you can work on the workshop problem of chapter 3 and chapter 4. And once after finishing the chapter 4, we can go over the workshop problem. Take it as a homework, all right? Thank you very much. Good night. See you tomorrow. Very good. Thank you. And if you have any questions, I'm still here. I would like to help you if you have any questions or doubt. If not, then we can take it tomorrow. All right? Very good. See you tomorrow at 7 p.m. Eastern Time again. Example 3.1. It's 3.1, right? Here, the best estimate for the shear strength parameter friction angle phi of the sand layer. Your elevation is given here, 776.5 to 771.5. That elevations represent this. This is your elevations, right? 775. So it started 776.5. This is 770. So this is 771.5. So that is defining the layer of sand. When you look at the layer of sand, the n value is given here. Okay. Therefore, based upon this, n value is 12. 5 plus 7. So if you look at the table 3.3, that will give the strength of the cohesionless soil. Cohesionless soils is sand. Sand is a cohesionless soil or granular soil. So for the n values of 12, which lies here, your friction angle varies from 30 to 40. Okay, therefore 28 cannot be the answers because this is less than 30. 42 cannot be the answers because this is more than 40. 49 is greater than 40, therefore the only answer is 35. Okay. Okay. B. This is B, right? It has says estimates the unconfined compressive strength in kips per square feet for the fat clay. So if you look at the end, which is at a depth of 3.5 to 8.5, in the boring log given there, this is your depth, right? So from 3.5 to 8.5, this depth is your fat clay here. In your fat clay, the question asks is unconfined compressive strength. The QP is unconfined compressive strength. For the fat clay is 0.25. And we know 1 ton is 2 kips. Therefore, to convert this ton to kips, multiply this 0.25 with 2. That will make you 0.5. 0.5 KSF. Square feet remain as it is square feet. Okay. Patrick, you are good, right? Thank you. Good night. Jeffrey, there is appendix for the School PE's exam review guides also. There are equations given there, everything is at the end. All the equations, appendix, and reference tables. But if you already have a sum, that's very good. You can stay with that sums. It's up to you. We have made it for the handy, for the exam purpose. Okay? Alright, see you tomorrow. If there is no more questions, see you tomorrow then. Good night.